Okay, there we go. Good morning, or well, whatever time of day you're watching this. This is try number 3 to do your 10.3 thermochemical notes. So, thermochemical. So we're going to talk about writing chemical reactions that have to do with heat. There's really two main types that you've heard about before. There are endothermic reactions and exothermic reactions. And we talked about these before. Endothermic means heat is going into the reaction. So heat is a reactant in the chemical formula, something that needs to be added to then make the products. In exothermic, heat is a product. So it's going to be written on the left-hand side of the arrow. It's something that as we go through the reaction, that's going to make heat or give off heat energy. So let's start with enthalpies of reactions. Remember, enthalpy or delta H is the change in heat energy for a reaction from start to end. And we can define this, as the quantity of energy transferred as heat during a chemical reaction. These are known amounts for different reactions, and you can look them up. If you have your lab manual, it's going to be on page 93 of your lab manual. And if you have your textbook, it's going to be on page 862. When you go to those pages, what you're going to see is the first or the top half of the page are enthalpies of reactions for formation, which we'll talk about in a moment. And then on the bottom are enthalpies of combustion, which we'll get to after formation. So speaking of formation, that means to form something from its simple elements. So if we look at our example here, we have 2 hydrogens and 1 oxygen forms 2 waters and 483.6 kilojoules of heat. We're forming or producing heat, so this is an exothermic reaction. Another way to write the enthalpy of an exothermic reaction is to say the enthalpy is negative 483.6 kilojoules. Negative meaning we're giving out heat, we're losing heat to the surrounding environment. If we reverse that reaction, if we say water forms or splits into hydrogen and oxygen, notice how now our energy is on the left-hand side or the reactant side. So that tells us this is an endothermic reaction, something where heat is required. Heat is a reactant as part of our reaction mechanism. We would write this enthalpy as a positive 483.6 kilojoules. Now, where did I get this 483.6 kilojoules? Again, if you go look at page 93 in your lab manual and you find water as a gas, you will see that number 483. So what's important here? Well, the coefficients are important here. They represent moles. The state is important here. If you look in your lab manual, you'll see that there's an enthalpy for water as a liquid and an enthalpy for water as a gas. So the amount of energy really depends on whether we're a solid, a liquid, or a gas. Also, the enthalpy is proportional to the number of moles. That means that whether you have 1 mole or 2 moles, that matters. If you have 2 moles, you'll have twice as much energy as if you had 1 mole because they're proportional. Okay, so 2 types of enthalpies that I want to talk about today. The first one is enthalpy of formation. That's like the example we just looked at, where we form a compound from its individual elements. All of our elements are going to be monatomic, or just them by themselves, unless they're one of our 7 diatomics. Remember, have no fear of ice cold beer, or hydrogen, nitrogen, oxygen, fluorine, fluorine, bromine, and iodine. Those 7 elements will always appear in 2s when they're by themselves. So those are our diatomics. Now, balancing these equations are going to be a little different than what we've used before because we have this requirement. We must have 1 mole of the compound. That means we're going to use fractions to help balance some of our other single elements. Let me show you. I'm going to do the middle example, iron 3 oxide. Now, iron 3 oxide, this tells us that iron has a +3 charge. Oxygen, we know from the periodic table, has a -2 charge. I'm going to write it from its parts, and I'm going to leave space for balancing. So iron, which is a solid at room temperature. How do I know the state of matter? If you look at a periodic table, say the one in your textbook, or like dynamic periodic table, if you do a Google search for dynamic periodic table, tells you what state it's in at room temperature. Iron, solid at room temperature, plus oxygen, which is a diatomic, and a gas at room temperature. That shouldn't be surprising. Yields iron oxide. We're going to do crisscross. Oxygen is a +2, iron, or excuse me, a -2, and iron is a +3. So when we do crisscross, we get Fe2O3. Ionic compounds are always solid at room temperature unless told otherwise. Now that I've written it, before I balance, I'm going to go to page 93, and I'm going to look for solid iron oxide. And what I see is negative 824.8 kilojoules. Negative means exothermic. Negative means I'm going to place it on the product side. So I'm going to go plus, because it's part of our reaction, 824.8. I didn't quite leave myself enough room, so we'll squeeze the kilojoules in there. All right, next step is to go ahead and balance. Our compound must be 1. So 1 Fe2O3. That means I need 2 irons on the right side. I need 2 irons on the left side. I have 3 oxygens on the right side. I have 2 oxygens on the left side. How the heck? Oh, here's what we do. I need 3. I have 2. 3 halves. The 2's cancel, and now I have 3 oxygens on each side. So I know it's a little weird to think about using fractions because you could never do that before, but it's because we have this rule that we must have 1 mole of the compound because our enthalpies are proportional to the number of moles, and they're all written assuming we have 1 mole of that compound. Now I'm going to recommend you pause your video here and try writing the formations of carbon dioxide and sodium nitrate yourself. Write out the formation, then look up the enthalpies, then balance. Go ahead and pause now. All right, when you're ready, here's the answers. Carbon dioxide, we have solid carbon and oxygen gas. Yield carbon dioxide gas with an enthalpy of 393.5 kilojoules. And this balances out with coefficients of 1. Sodium nitrate, we have solid sodium and diatomic nitrogen gas and diatomic oxygen gas forming sodium nitrate solid. And let's make a little more room. That over a little bit. And our enthalpy is 467.9 kilojoules. Again, these were all exothermic, which is why they all ended up on the right side of the reaction. Now, to balance this one, we need coefficients of 1, 1/2, 3 halves, and 1. All right. So that was formation, or forming a compound from its parts. Now we're going to look at the enthalpies of combustion, or in other words, burning some fuel in oxygen gas to form the products carbon dioxide and water. So those are going to be constants. Our rule that we have again is we must have 1 mole, this time not of our forming compound, but of our fuel from combustion. So if you look at page 93 in your lab manual or your page in the textbook, at the bottom, you're going to see enthalpies of combustion. And we can find butane on there. And the enthalpy for butane for combustion is a negative, or exothermic, 2,877.6 kilojoules. So let's go ahead and write our combustion reaction. Our fuel, butane, which is a gas, and oxygen gas will form, let's leave some room for balancing, will form carbon dioxide gas and water vapor. We'll put water as a liquid. And we also need to put in our enthalpy. Never leave myself enough room. Let's squeeze that in there. Kilojoules. All right, so that's like we did before. Now we're going to balance it. We must have 1 of our fuel. So we have 4 carbons. We need 4 carbons. I need 10 hydrogens, so we'll put a 5 over here. Now I have 5 times 2, 10 hydrogens. Now I need to balance my oxygens. 4 times 2 is 8, plus 5. I have 13 oxygens on this side, and I have 2 on the other side. So how do I balance this? 13 over 2. So that's how we write enthalpies of combustion. It's just remembering we have our basic formula, fuel plus oxygen yields CO2 and H2O, and we balance to have 1. Always leave oxygen for last when balancing. All right, the last thing I want to do today is review some more heat stoichiometry. Don't freak out. Stoich is our friend. All we're doing is we're changing from units of one thing to units of another. So we looked at the combustion of butane, and now we want to actually find some information. Well, how much energy do we need to involve if 78 grams of carbon dioxide are produced? So what we want to look at is we want to start with what we know. We have 78 grams of CO2. Now, grams is never really useful to us in stoichiometry. We always need to change to moles. How do we change to moles? We use the molar mass. The molar mass of CO2 is 44.01 grams for every 1 mole. So that's 12.01 for carbon and 16 twice for oxygen. Once we have moles, we want to change from moles to kilojoules. To do that, we are going to use our enthalpy. Now, our enthalpy is negative 2,877.6 kilojoules for every 1 mole of the butane. Well, for every 1 mole of the butane, there are 4 moles of CO2. So what we're going to do here, there are 4 moles, the coefficient of CO2, for every 2,877.6 kilojoules of heat energy. It is proportional to the number of moles. Once we're here, go ahead and pause and try this on your calculator. Check that you can get the same answer as me. I'm going to go ahead and get my calculator out right now. When we do this, I'm going to take 78 times 1 divided by 44.01 times 2,877.6 divided by 4. And I'm going to get 1,275 point on and on and on, but I have 3 sig figs. So my answer is going to be 1,280 kilojoules, or in scientific notation, let's write that more clearly. 1.28 times 10 to the third kilojoules. All right, go ahead and try more of these on your 10.3 worksheet. Great job today, guys.